Hi, let's take a look at a problem that we could address using kinematics in two dimensions, but which energy conservation makes our lives much simpler. So, say there's a plane that's flying at an angle of 30 degrees above the horizon at 240 meters per second. And when it's at a height of 1,240 meters, it releases a package. Now, if we want to figure out how far the package goes, we'll need kinematics. If we want to figure out the ultimate height that that object goes to, we're going to need kinematics. But if we just want to figure out how fast the object is going to be traveling, we can use conservation of energy. So let's figure out how fast that object will be traveling just before it hits the ground. So when we look at energy and consider what all types of energy are there, well, we have motion, so we have kinetic energy, and we have potential energy due to gravity, and that's it. No other forms of potential energy. So if we're just dealing with the potential energy due to gravity, we're free to call zero potential energy anywhere we want in the universe. So it's always a good idea usually to call the lowest point in your system zero potential energy when we're dealing with gravitational potential energy in the form of the weight of an object times its height. So just before the object hits the ground, it'll have no potential energy. It'll have a kinetic energy of 1/2 times the mass of the object times the final speed squared. Now at the top, right when it's released, it has a gravitational potential energy equal to the mass of the object, the strength of gravity, and the height of that object. And since it's attached to something that's moving, it also has kinetic energy equal to 1/2 times the mass times the initial speed squared. So the total energy at the top is going to be the gravitational potential energy, mgh, plus the kinetic energy, 1/2 m times v initial squared. So, by energy conservation, if there's no loss, the energy at the bottom equals the energy at the top. So, 1/2 mv final squared is going to equal mass times gravity times height plus 1/2 mv initial squared. And the first thing that we can do is get rid of all of those masses. Just like in kinematics, mass doesn't matter. With energy conservation, mass shouldn't matter under the same assumptions, and it doesn't. So when I multiply everything by 2 and then take the square root, I would find that the final speed is going to be equal to the square root of 2 times gravity times the height of the object plus the initial speed squared, and that value is going to give me 286 meters per second. Now again, this is just the speed. I cannot figure out the direction without having additional information, and if you need the direction, if you need the distance in the x direction it's traveled, if you need the ultimate height of the object, kinematics is probably going to be your friend. Thanks for watching.